Hello everyone, my name is Ben, and together with Pascal, Joel, and Anne, we've completed this propeller design project. The presentation will consist of the following major categories. First, we will have an introduction describing the project. Next, we will discuss different types of propeller theories. Following this, we will analyze the process we went through to come up with our final propeller design. Following that, we will describe the results of our testing process in the wind tunnel. Next, we will have an error analysis where we describe the reasons for potential difference between theoretical and experimental results. Following that, we will talk about influencing factors, such as number of blades, and delve into more details involving propeller efficiency. Finally, we will have concluding remarks.
The objective of this study is to look into the design theory and build a propeller model according to the requirements. So first we begin with the initial calculation, and we establish a CAD model and manufacture it by the 3D printer. The wind tunnel test is then carried out, and the data and its error is analyzed. So here we got all those design requirements, like the static thrust of 0.2 newtons at 5,000 RPM. We have to get the maximum efficiency at the velocity of 5 meters per second at 9,000 RPM. We also need to consider the minimum mass of the propeller, and all those environmental constants are listed there.
The basic theory that we start with is actuator disk theory, also known as momentum theory. This theory states that for an incoming stream, the velocity will be increased after the rotating disk. The next theory, impulse theory, takes into account the rotational induced velocity after the disk. The blade element momentum theory builds on both of these and is now applied for the specific case of a propeller. And now this takes into account the number of blades, airfoil characteristics, like lift and drag, which can be obtained for different NACA airfoils using software like Xfoil.
Based on our research, a common airfoil profile used for propeller blades is NACA 412, so we used Xfoil to obtain CL over CD curve versus angle of attack for a selection of airfoils close to NACA 412. From the plot, it is observed that NACA 410 has the best performance and optimal weight, so it was picked for our design. We calculated that the propeller will be tested with a Reynolds number from 5,000 to 40,000, so the same curve was then plotted for NACA 410 at different Reynolds number. The data were used in the following calculation process.
After the airfoil selection, we began with the design process. We used the McCormick method, which is based on the blade element momentum theory, but it's a little bit different. We got the constant pitch, and we assume that it's a constant pitch and a constant chord length, and then we begin all those calculations and manipulation of the formulas. Then the induced angle of attack is obtained in the red brackets below with all those parameters. With this induced angle of attack, we can calculate the elemental thrust coefficient and the power coefficient. Instead of integrating them, we can use the discretization methods to calculate each section of the blade, and we can get the total thrust coefficient and power coefficient to get the efficiency. So after various trials, we found out that the pitch should be this value, and we also use the linear chord length to avoid some tip vortex loss. The maximum efficiency is obtained like 0.52 at the advanced ratio of 0.256, which is shown in this illustration on the right.
With the stated design process, blade cross-sections at several locations were defined by their chord length and pitch angle. The CAD model was then built with propellers blade formed by these cross-sections and the cylindrical supporting blade. A brief structural simulation was also carried out with the mesh setup as you see here and the simplified uniform load. The stress and strain distribution appeared to be within material limits. The model was then 3D printed and ready for test.
The test result. We mounted the propeller on a motor inside the wind tunnel for 2 different experiments, with the wind tunnel running at 5 meters per second and for the static case at 0 meters per second. The wind tunnel testing was carried out on November 21st, where we placed the propeller on a sting to get the lift and drag measurements. However, at first the propeller did not fit on the mount. We got creative in increasing the whole size of the propeller so that it could be properly fitted. We did have difficulties, but we kept trying. After a few more attempts, we finally had some success. And we were able to mount the propeller and get measurements. As you can see here, the propeller spun just beautifully. The results. For the first experiment, we were hoping to get a static thrust of 0.2 newtons, and we achieved a thrust of 0.113 newtons. For the second one, we expected to get maximum efficiency at 9,000 RPM when the wind tunnel was running at 5 meters per second. We achieved our maximum efficiency at 8,000 RPM. However, this maximum was just 0.001 higher than what we received at 9,000 RPM, so it was quite close. Comparing our theory with our empirical values, we see that we're significantly less efficient than we theorized. One other important note is that we did not have any structural issues once we were doing the wind tunnel testing.
We can think a lot of errors that contributed to the differences of test results and expectations. One major one is tip loss caused by the vortex formed at blade tips. This could be resolved by adding Pringle tip loss factor to the calculation model. Another factor is the wake at downstream of the propeller, which would make the downstream velocity different from what we use in the calculation process. Other issues also occurred during the test. For instance, the high rotation speed and free-stream wind condition created a lot of vibration and deformation of the propeller blades, which led to a change of pitch angles from the static state. And the wide blade tips in our design made it worse.
Other influencing factors. Some additional losses could be possible from manufacturing error, as we had a slight crack after the 3D print, and we had to add some glue. Testing error, we don't believe this was a significant factor. But other important parameters, the Reynolds number, lift will be higher at higher Reynolds number. The blade number, which for us had to be fixed at 2. As you increase blade number, you might get increased power. However, there is interference, and therefore efficiency goes down. We saw that the advance ratio is linked to the efficiency, both empirically and theoretically. And then the angle of attack, which has a big effect on the lift, which we were able to vary through the pitch angle.
Alright, so here we come to the conclusion. We begin with the basic theory of the propeller design, and we select the airfoil that is optimum for our case. We then calculated with the McCormick method based on the blade element momentum method to select the pitch and the chord length for required thrust coefficient and the efficiency. The CAD model is then established and a simple structural simulation is carried out later on. After the 3D printing of this propeller, we tested at the static thrust and the dynamic thrust case with various RPM. But it seems that the result is not satisfactory, so we analyzed all those errors that may cause our problem, and we also analyzed all those influencing factors that may affect this propeller to be less efficient.